Welcome to our third day of July 4th. Thanks for joining us. So it's an honor to have with us today Professor Alexander Barg from the University of Maryland College Park, where he is a professor in the Department of Electrical and Computer Engineering and also in the Institute for Systems Research. I hope I got that right. And then, so some of you probably already know Alex, or Sasha, from his role as the editor-in-chief of the Transactions on Information Theory. He's also won a number of paper awards for his work in broadly speaking coding theory. Some of that you'll hear about today. So he won the IT Society Paper Award, the Data Storage Award, and he's also been a plenary lecturer at ICIT. So if you're at ICIT in Barcelona, you already heard such a plenary talk there. So it's great to have him with us today, and we're really looking forward to it.
Thanks very much for the invitation, for organizing this school, and thanks for having me on this holiday, the 4th of July. I appreciate all of you showing up, and don't mind those who didn't. I need to do something so that it doesn't go out. Huh? Sorry, I forgot that thing. There is this little app called Caffeine. This presentation is about erasure codes for distributed storage, and while indeed this is the title, the distributed storage is more of a motivation than a real goal of these constructions and derivations. And the main message of this tutorial will be given on this first page, and it says that as we look at distributed storage, or as we started to look at that, we isolated a number of problems that had been previously unrecognized, and the problems called for new techniques and new ideas throughout coding theory, information theory, and neighboring areas, computer science, discrete math. And a large volume of work throughout the past decade. As you will see, of course, I will reference only a small part of them. And the idea is to introduce these methods, introduce the associated results, and to point out the problems that I see both interesting and important for future work. To begin with, I will acknowledge my co-authors in these works throughout a good number of years, starting with Itzhak Otsahitamo, currently from Tel Aviv University. Minye is a postdoc at Princeton. And, sorry. Chen Zitan is a current student. And Serge Vladuts, who some of you may know from his long line of work on algebraic geometry codes, is a professor at University of Marseille, on leave from his job in Moscow. Right. So this is a data center as lifted from this web page at host2be.com. What did I do? Nothing, huh? Okay, thank you. Very good. So this is a data center. This is where your Instagram pictures sit when they go someplace. And there are specifications at the bottom of the screen. And there is a multitude of technical problems. But of course, one of the significant issues here is that those drives often fail just because of the sheer volume of the operation. And as they fail, we need to make provisions for safe storage of the data. if you visualize this data center as carrying a large volume of data, such as this one, spread across the drives that you saw in the picture, so this is the storage drive, 2 terabyte drives that carry those pictures, then the data is spread across thousands of storage nodes, and of course the nodes fail frequently simply because little p probability of failure. As you multiply by the number of nodes, Pn becomes large. Right? And of course we rely on erasure codes, or we should rely on erasure codes. So this is the prevalent method, or at least a mainstream method that they use to protect the data centers from losing information. What do? They write the data several times, right? Replication. So data, and then replication, triple replication. And this works very well for a time being, right? Because it is very easy to recover the lost data. But the storage overhead becomes a factor of 3, and at some point it is difficult to maintain the system. The volume of the data requires other solutions. A competing idea is, let us take, let's say, 3 data nodes and add 3 parity nodes, meaning that we take 3 symbols from the top nodes and add 2 parities, and do that for every triple of the symbols on the data nodes, right? So let us say they're encoded with an MDS code of length 5, and this is the number of data symbols 3. So this thing can tolerate, again, any 2 node failures because of the properties of the code that we shall discuss in more detail a bit later. And the storage overhead is now 5/3, which is 1.67, which is less than 2, or less than 3 on the previous slide. So this is better than replication in that respect. Block-based system model. Well, it just says that the data blocks are encoded independently. Nothing much. Let's skip that for the time being. So we compare replication and the MDS solution, and we see that while we have gained in the storage overhead, where we are losing is the network traffic or network flow. To recover a lost node, we need to carry the amount of data that is exactly stored on that node. Whereas here, as we recover a lost node, we should take 3 nodes to correct the data by the properties of the code. So the network flow is triple the size of the data, and here the network flow is equal to the size of the data. So while we have gained in the storage, we have lost on network communication, and that's also an important factor because, of course, the network gets saturated and we will lose the functionality because of that. So this is where this whole story develops. It's between this storage size and the network traffic. And as we make these problems more precise, we isolate specific research questions, and then we offer solutions. This is one of the first solutions by Cheng Huang and co-authors for Windows Azure Storage 2007, and that was before all of these concepts have been isolated and defined in coding theory and the coding information theory community. They just said, let us have a parity check for 3 symbols, and that will correct a single erasure, single lost node within the 3, or single lost node within these 3, relying on this local parity check. But if we lose 2 nodes, we go to global parity checks. So the network traffic, when we lose just 1 node, is smaller compared to a larger loss. And that was really a good idea in practical terms, and that is one of the sources, one of the starting points for the development of coding for distributed storage. A similar solution, another similar solution again with 2 local parities, 2 global parities. These are simply the parameters that were actually used in Windows Azure. That's why this picture appears here. They call them pyramid codes. That was not a general solution, but it was really a clever practical idea that moved the whole development forward. The main ideas were laid out in the following foundational papers. So repair degree refers to the number of nodes, not the traffic volume, not the storage overhead, but the number of nodes that we have to contact to recover the lost data. Call this repair degree. That was put forward by Huang, Parikshit Gopalan, Simichi, and Sergei Hanin. And that is the Transactions paper 2012. It became known already 2 years back before that, and it gained popularity and awards and whatnot. And it spurred a large volume of work on codes with locality. Right? So the Huang's paper is acknowledged here. That was 3 years before the preprint of this paper was released. Repair bandwidth is the same as network communication, so that is the second metric. Repair degree, repair bandwidth. And that was isolated in a foundational paper by Alex Dimakis and co-authors, Transactions, again, Information Theory 2010. And under the, yes, and again, a large volume of work, and yesterday in the poster session, there were quite a few devoted to the variations of these basic questions, so this is still a living and developing direction, right? And within that topic, there is a smaller subtopic, but yet original and also of interest by Venkat Guruswami, Mary Wooters, and that specifically refers to Reed-Solomon codes. Reed-Solomon codes are a very popular family of codes, still in use, still being researched, and I will speak of those as well. So this third paper comes within the framework of the second one, and yet it is original, novel, and important. So this is where the main ideas come from. Out of them, there were hundreds and hundreds of papers, probably approaching the first 1,000. Well, of course, it's difficult to count, but if you look at this survey here by Balaji and co-authors on arXiv last year, maybe by now already published. I think it was submitted to Science China. And you will see hundreds of references, and they drew this very nice picture of variations of the problem that I simply lifted from that paper. So this is, let me see what it says. Yes, so the bandwidth is on the left. The repair degree is in the middle, and then there are variations of these questions, and so on and so forth. Reed-Solomon codes are here, and there are other problems being considered. All right. Current literature count in the hundreds. This is the outline, and I'm sure, as always, I have over-prepared, but I will skip some parts when I see that it doesn't fit in the time. But this is what I would like to discuss. So locally recoverable codes, constructions for lower the repair degree, related problems, and open questions. For the first part, so the open questions will not be exactly isolated closer to the end. I will mention them as they arise. And in the second part, I discuss repair bandwidth. Well, these catchwords have to be defined carefully, so let me not read them now. We'll discuss them later. Heterogeneous storage. And then I will mention in the end where, in my view, this could develop. Of course, you may disagree, which is fine. But I have an idea of where this direction as a whole is moving, and I would like to suggest it to your attention. All right, so let us go back to the very basic question of correcting just one erased coordinate. Very basic coding solutions say that, well, pretty much any decent code will correct a single erasure, right? This is what we are discussing. One storage node has failed. We spread the coordinates across the storage nodes, and a failure of the node amounts to having introduced one erasure into the encoding. And this is the condition when a code corrects one erasure. And as you see, if the code is not completely out of whack, it will correct one erasure, so the Hamming distance 1. So let's consider this binary code with this parity check generator matrix. We encode 3 bits into 7 bits of the code. We take those 3 bits, multiply by the first, by the second, by the 7th column, and this is the encoding. So we have encoded 3 bits of the data into a 7-bit code world. All right? It will correct one erasure. It has distance 4. So any 4 bits of the code word identify the code word uniquely. Take any 4 bits here. There is just one code word that fits these 4 bits. So the code corrects 3 erasures. But to correct 3 erasures or to use the global correction properties, we need to get to 4 bits, as said here. Let's say we just need to correct 1 erasure. This is a new question, right? You look in the textbooks on coding theory, and it is not mentioned. So what do we need to correct 1 erasure? 1 erasure can be recovered from 2 bits, such as this one is this plus that. And so if this node is lost, then we recover it by computing this parity C4 plus C6. If you are familiar with this, I will mention this briefly. Of course, this is a dual of the Hamming code, called itself the simplex code. And locality is due to the fact that the Hamming code words of the minimum weight in the Hamming code carry a Steiner system, Steiner triple. So if you know that, then you know the reasons for that. But it doesn't matter in this context. The fact is, the point is that to correct 1 erasure, we need to contact only 2 bits and not the 4 bits, as the standard coding solution would suggest. So this is locality. So we are interested in efficient representation, implementation of erasure correction in storage applications. The terminology comes from those applications. As we said, the coordinates of the code word are called nodes. So we say a node, we mean coordinate. A node is erased, we say it's failed. We go to some of the surviving coordinates, as in the example, we went to C4 and C6, and call them helper nodes. And moving information is termed downloading, right? So we have changed the language, but not the substance. But we have to remember these words, because otherwise it is not clear what is being discussed, right? Because mathematically, the word download is not defined, but it is just the change of the language. Let us go take a brief reminder, right? If you have seen this, I apologize, but if not, maybe as a quick overview, this will be useful. So what's a finite field? A field, such as real numbers, is a system of elements that you can add and multiply, and also importantly, subtract and divide. So they are closed under two operations, addition, multiplication, but also they have the inverses. So they form, there is a multiplicative group and there is an additive group sitting in the background. And there is the 0 element for addition that is called 0, and there is the 0 element for multiplication that is called 1, and so on. So it is possible to divide if we take integers modulo 13. If 6a is 2, then to find a, we take the inverse of 6 mod 13, and the inverse of 6 is 11, because 6 times 11 is 66, and mod 13, that's 1. So therefore, 11 is the inverse of 6. And so a is 11 times 2, mod 13 is 22 minus 13, 9. So that's how we solve equations. That's how finite fields work. A field, well, that's OK. We already have said that. Finite fields exist for any size, for any cardinality q, which is a power of the prime. So 13 to the power 1, or 2 to the power 6, and so on. And for any given size, the finite field is unique, meaning that it is not possible to construct two different fields that are not isomorphic to each other. And what is the most important is that linear algebra works over finite fields pretty much the same way, not exactly, but not that far from the way it works over the reals or any field of characteristic 0. And polynomials work too. So there are zeros of polynomials. There are basic theorem of algebra that says that the number of polynomials does not exceed the number of roots does not exceed the degree, and so on and so forth. Another reminder is Reed-Solomon codes. Reed-Solomon codes are defined over finite fields. So it is good that we have reminded ourselves of those. Let us say we have four symbols of data. I'm now not using the word bits because the field will be of a larger size. So 4 symbols of data from some finite field. We need to encode them into a code word over its Solomon code. As we did before, we encoded 3 bits into 7 bits. So let's encode these 4 symbols into some number n of symbols. We take n elements in the field, p1 to pn. We form a polynomial where x is an indeterminate here, and an unknown. So we write a0 plus a1x, a2x cubed, a3x3. And then what we do, we take that polynomial and evaluate it at the isolated elements of the same field, p1 to pn. Right? So we visualize a graph. There's something wrong there, right? I know it's not my eyesight because I recently passed a test for driver's license, so I'm good. All right, let's look here. No, let's not. So we are evaluating those polynomials at the points of the field. And visualization is difficult because it's a finite field, so there is no continuity, but it is difficult to draw it otherwise. So let us kind of assume we could draw something. And we evaluate f at p1, p2, pn, and those evaluations, n tuple of the elements of the field, form the Reed-Solomon code word that is associated to the symbols of the data. In the background, there is a choice of the p's. How do we choose them? Well, in a suitable way to be discussed, to be mentioned as needed. So that's the Reed-Solomon code. Now, this is a polynomial, and as we said, it has degree 3, so it can have at most 3 zeros. So the at most 3 values can be 0, so n minus 3 values are not 0. And so the minimum Hamming distance of this code is therefore n minus 3. And it is the best possible according to the singleton bound. So an RS code is a set of vectors obtained by evaluating all polynomials because the a's can vary. So there are q to the 4 possible data vectors. And of degree k minus 1 in general. So k here, therefore, is 4. K minus 1 is 3. Degree is 3. K minus 1. The minimum distance is n minus that, as we just discussed, n minus k plus 1, which is the maximum possible according to the singleton bound of coding theory. And a code that has Hamming distance equals the length of the code minus dimension minus 1 is called a maximum distance separable code, MDS code. Reed-Solomon codes form an example of MDS codes. It's a linear code of length at most q minus 1. Why is the length restricted? Well, we needed to choose the points p1 to pn, and there are at most q minus 1. Well, let's ignore 0, non-zero elements in the field. And so the length of the code is limited to q minus 1. Given a polynomial, we construct a code word as described on the previous slide, and again written here in this equation. So this is a formal definition which does not say anything else on top of what has already been said, except expressed in mathematical terms. We define the evaluation map, and we form a code vector. So a Reed-Solomon code is a linear map of a k-dimensional vector space over the field onto the n tuples over the finite field fq. Example, well, we already did an example, but I did here a calculation for a field of 8 elements. And again, alpha is a primitive element of the field, and we form a polynomial. So I chose 1 alpha for the data, and this is the code word that is obtained in a discussed way. Now, what's wrong with the Reed-Solomon codes now that we said that they are so good? Let's say we take the 1410, this Facebook code, called Facebook because it's installed there. 14 is the length, 10 is the number of the data symbols, and the field in the background is of size 16. All right? So there are 10 symbols of the data, 4 parities. It does not have to be systematic, but of course, systematic means that the data symbols enter the encoding without changes. And so the only thing that we change for the encoding is the parity symbols. So loss of a node of this node triggers the repair task. And as we see here from the description of the code, we need to carry information from 10 nodes to recover a lost node. And transmitting the information from 10 nodes is a lot of traffic. So it generates tenfold as much traffic as the replication solution. And therefore, this is clearly a limitation of the Reed-Solomon code. And if a large portion of the system is a Reed-Solomon encoded, then the network saturates. So that's why we are not happy with this solution. Our goal, therefore, is construct more efficient solutions for the task of a single node repair. This triggers the definition of locally recoverable codes, LRC, or locally repairable codes, sometimes called, so an LRC code. NKR, R is the third parameter, hitherto undefined. So N and K, N is the encoding length, K is the number of the data symbols. We take K data blocks and produce N blocks as before, as in this picture. Let's say there was one erasure. Every symbol in this LRC code is supposed to have a recovering set, as a set of helper nodes. So that set is Ri, of size R. So the idea is that we recover that erasure by turning to R other symbols in the encoding, where R is much less than K. So this is local repair. Instead of looking at K symbols that would give us the entire code word as 10 in the previous example, we look at 2 or 3, and we strive to recover the one lost symbol from looking at a much smaller subset of symbols. That is the LRC code. So this is the new node that we are trying to recreate. This is the new node, and it looks at R symbols in the encoding and recovers its value, if that functionality is provided. Our first goal is to see how to provide that functionality. Well, every code has locality K, trivially. You should try to think why that is true. Why is it possible to always recover one erasure from looking at K symbols in the encoding? It's not 100% obvious, but it's not that far from that. So think why this is true. And while you're thinking, let's discuss the parameters of LRC codes. So our goal is to have R between someplace between 1 and K, not equal to 1, not equal to K. We will assume that R divides K, the number of the helper nodes, and R plus 1 divides N. These assumptions are for technical purposes that are not that terribly restrictive, but they make presentation much more convenient. So what's the largest K over N, the rate of the code? Can we attain very large rate? Well, no. And what is the minimum distance? Let's try to answer these questions quickly. So the rate is bounded by R divided by R plus 1. In the standard encoding, you take any channel you can think of, the Gaussian channel, or whatever your favorite channel, the Poisson channel. The rate in principle could be as close to 1 as you want. For LRC codes, it cannot. And if the size of the repair group R plus 1 is 3, then the rate is at most 2/3. So that is what we pay in terms of the rates for having the locality property. This is easy to prove. Well, not to prove, but to almost prove. There are some subtle details that will not be mentioned. But morally, the following argument should be clear. At most, that many coordinates determine the entire code word. Why is that? Well, because some coordinates are dependent on the other coordinates, right? Expose the values of coordinate in a recovering set. There are R of them, little r of them. 1 comes for free. Then repeat this. Again, take another recovering set. And upon exposing at most that many coordinates, we have recovered the entire code word. Right? So there are dependent symbols. That's why the rate cannot be high, very high. All right, that's the rate. This bound is tight because we can construct codes of that rate, specifically partition the k bits into k over r groups of size r. We have assumed divisibility. Attach a parity check to every such group, and that is a locally recoverable code of the rate exactly r divided by r plus 1. So even over F2, the field of 2 elements, this bound is tight. All right, so the minimum distance, this is the famous Gopalan et al. Bound, sometimes called the singleton-like bound, because if we take r equal to k, we get n minus k minus 1 plus 2, so n minus k plus 1, and that is exactly the singleton bound. So this singleton-type bound for linear codes in the first paper, in the general case in the second paper, is a natural upper bound on the distance of LRC codes. So the distance, again, we pay in terms of the distance for having the locality property. Reed-Solomon codes would have higher distance, but Reed-Solomon codes do not have locality. So we retract a little bit in terms of the distance by k divided by r, and we may gain locality. Smaller locality, lower failure resistance, because it is easier to knock out 2 coordinates within a repair group, and generalization of the singleton bound already mentioned. A code is called optimal LRC if that distance is achieved with equality. So why optimal? Well, Reed-Solomon code is optimal, are optimal, and therefore we might be interested in constructing codes that meet this bound with equality. So optimal LRC codes achieve this bound with equality. There is a proof of the distance bound. It is slightly more technical. I will not go over this slide. But the idea is, again, this dependence of coordinates. We isolate. All right, pictures are being taken. We isolate a subset of coordinates that exploits the dependence structure imposed by the locality groups. And this argument would give the bound on the previous slide, as described here in more detail. I will not spend time on that. This is their famous result, Gopalan et al. And of course, it's accessible from many sources. Again, the thing to remember is that we have to pay in terms of the distance for having locality. All right, so there were some early results on constructing optimal LRC codes. Early constructions were not particularly explicit, and the underlying field had to be of a very large size. Why is it bad? Well, because large field, again, implementation complexity, and therefore it is preferable in the system to have Reed-Solomon-like construction where the size of the field is comparable to the length of the code. NSQ, and not super polynomial or even exponential in n, right? Because that would be more difficult to install. Again, one of the first constructions for this specific choice of parameters were provided by Vijay Kumar and his students as early as in 2012. There were some explicit constructions over large fields for any parameters but large field, as I said. And before introducing a construction I would like to discuss in more details, let us discuss some easy cases. So locality k. As we said, most codes have locality k. The distance, the bound, tells us that it is at most n minus k plus 1. Reed-Solomon code is an optimal nkk, where the second k is for size of the the number of the helper nodes. And the size of the field is pretty much the length, or bounded above by the constant times the length. So this is for k. For 1, well, for 1 we can do the following. This is what the bound would tell us. And we can take Reed-Solomon codes of length n over 2 and attach another Reed-Solomon code word of length over 2. So this solution will give an optimal LRC code of length n dimension k and locality 1. The field size is again good. So the question is, therefore, what happens between 1 and k? We have constructed optimal codes for the boundary cases. What happens in the middle? Let's try to look what happens in the middle. So this is the Reed-Solomon code word. The data symbols, the parity symbols And if one erased value, if one node is erased, this one, then we need to read k values of the encoding. And we want to read fewer. How do we do that? So to recover the entire code word, we need to interpolate a polynomial of degree k through the points p1 to pn, through the evaluation points. But we only need one coordinates. Is it not possible to do something more clever than recovering the entire code word? Well, suppose that this polynomial could be restricted on a smaller set and become smaller degree polynomial. If that's possible, then that would be a good idea to construct the code. So what if we can interpolate a low degree polynomial through the lost point? It is probably possible, easy to do for one lost point, but we want this for every point. So 3 points are connected. If this one is lost, we again could interpolate this low degree polynomial. And of course, this is a drawback of my visualization because through 3 points, I guess it's okay, right? Never mind, I know what is going on, it's fine. So low degree polynomial. And the message is it is possible to construct codes by taking carefully chosen subcodes over its Solomon codes. This is what I'm going to present on the next slide in an example. Let us say we encode 4 symbols of the data, and we want our locality R to be 2. So every single erasure should be recovered from looking at 2 other coordinates in the code word. The field of size 13, as before, because it is easy to do computations in your head, computing modulo 13 is easier than manipulating with elements of the field of 16 elements. Let us say that the set of points p1 to pn are the elements 1 to 12. So we evaluated all the elements except the 0 element. Partition these evaluation points into 3 recovery groups, A1, A2, A3, as shown here. Let us say our message is of 4 symbols over the field of 13 elements, 4 as desired, and we index them A0, 0, 0, 0, 0, 1, 1, 0, 1, 1. Now let us evaluate this subspace of polynomials. Degree 0, degree 1, degree 3, degree 4. Degree 2 is skipped by design. Let us say the data is 1, 1, 1, 1. So our polynomial that we are evaluating is now of this form, 1x, x3, x4. And this is the code word. Let us say the value at 1, which is 4, 1 plus 1 plus 1 plus 1, so this is 4, is erased. We access the 2 remaining points, 3 and 9, within the same recovery set, 3 and 9. We extrapolate, not extrapolate, what is the interpolate, sorry, the polynomial of degree 1, because there are 2 points. So the polynomial that passes through 8 and 7 is 2x plus 2. Evaluate that polynomial at 1 and get back the erased coordinate. So this is how we can interpolate polynomials of smaller degree. In the example, let's see what is behind this construction slightly more generally. So what we do is the following. Remember, ultimately we need a polynomial of degree k minus 1 to encode k symbols. So we take a polynomial g that is constant on the repair group on every repair group of size r plus 1. For instance, the polynomial x cube is constant in our example on the chosen repair groups. 1 cube is the same as 3 cube, as the same as 9 cube mod 13. So 3 cube I still can compute, it is 27, and that's indeed 1 mod 13. But 9 cube, I checked that at home, that's also 1 mod 13. And you can check that this x cube is also constant on this set and on this set. And we encode our code word not with a polynomial of all degrees, but with a polynomial of this form, where g is our x cube. The x's are the loose x's that will bring our degree up to bring the number of coefficients up to k. So we evaluate that polynomial, and this is a subcode of an RS code, obviously, over its Solomon code. And it is easy to show that the parameters of the constructed code in general meet this Gopalan et al. Bound with equality, and this is all in our work with Zach Tamo from 2014. So that is how you solve the question of constructing optimal locally recoverable codes of over fields of a small cardinality. Reed-Solomon-like codes, subcodes of Reed-Solomon codes. All right? Yeah, this is a remark on how to construct polynomials that are constant on little subsets. So if you think of this, right, it is against our Euclidean intuition. A polynomial that is constant on segments of a real line must be a constant, right? Such polynomials do not exist. A function that is piecewise constant on a connected topological space is a constant. But the finite field is not a connected topological space. So there exist piecewise constant polynomials. And one way to do that is take polynomials of that form that cancel out subgroups of, let us say, the multiplicative group of the finite field. And they can be used in the construction. This is not the only way to do this. And other ways were shown in more than one paper by Sihem Ménager and her co-authors. I'm citing one, but there were more. So there are other ways related to this idea, but going beyond this idea of constructing these constant, piecewise constant polynomials. This is the overview of what I said. Take subcodes of Reed-Solomon codes of length n of that dimension. We start with RS code of that dimension and choose out of that code a k-dimensional subcode that gives us an optimal locally recoverable code. So this is as far as repair degree is concerned. This is not the end of the story. This is we are now jumping to the second part of the to later parts of the story. So I have presented this construction. These codes, by the way, are studied outside the storage context. You have some algebraic or some coding family. The list decoding question is, of course, very popular, particularly for its Solomon codes following the work of Venkat Guruswami Madhusudan. And along these lines, the presented family of codes was list decoded in this work by Holzbauer and Antonio Wachtertze a couple of years back, in fact, 1 year back, right? Now, a counterpart of the combinatorial question is the question of whether those codes are close to capacity, right? Because that's the question that they ask about codes. How do polar codes scale as we approach capacity? That's what people ask these days all the time. So how do LRC codes scale? Do we have to pay in terms of gap to capacity if we have locality? Yes, we do. Yes, we do. And this has been quantified in a nice paper by Arya Mazumdar, capacity of local recoverable codes. The erasure case, the BEC case, is resolved. We know exactly gap to capacity. The binary symmetric case is open. It doesn't appear that easy, by the way. I have tried, didn't manage. So what is the gap to capacity of LRC codes on the BSC? I don't know. LRC codes on graphs, specifically on graphs for Platonic solids, Platonic graphs. A nice paper by Swan and Kade, Rob Caldebank, 2 years back. So not necessarily the storage context. This mushroom, right, branch out into related questions. So this is overall a fruitful direction, right? There are generalizations. The length of the codes is limited to Q, of course, because again, we are choosing evaluation points in the field of 13 elements. There are at most 13. What if we want longer codes? Maybe yes, maybe no. But we can replace, we go back in history, what if we want longer QA codes? Well, we take more evaluation points. There are no more points in the field. How do we make more? Well, we take pairs. And that is the first step along the discussion of algebraic curves. We can construct LRC codes of large n and q. Are they optimal or not? Well, that's a separate question. More no than yes. But let us say we evaluate now at the set of pairs. Let's take these pairs, right, over F9, a set of pairs that satisfy that equation. There are 27 such pairs, and this is now the length of our code that we may be able to construct. We have to evaluate at pairs, so we need now bivariate polynomials. Let us span our set of polynomials by the following polynomial basis. Let us evaluate. And so, for instance, this is the message. This is my polynomial, the coefficients for the basis. We evaluate the polynomial at the pairs that satisfy that equation, and we get a code of length 27. If you are familiar with that, that is construction of evaluation codes on what they call Hermitian curves. The affine part of the Hermitian curve is precisely the set of points that satisfy the equation of this type. We can construct long codes, therefore. Are they needed in storage? Not particularly. So why are we constructing them? It's a natural question, because it had been looked at in coding before, and it kind of calls for it. So as you see, the logic of research takes you beyond the application, which in my view is what applied mathematics is all about. You start with a problem that is motivated by something that happens in real life, but then it develops according not only to the laws of the application, but also to mathematical laws of mathematical logic. I think that's a justified direction of work in applied mathematics in general. Now, what do people do when they try to prove capacity theorems and things like that? They look at random codes. What will happen for a random code? So let delta be the relative distance, d divided by n. Define the largest attainable rate of the code with distance delta, lim sup of that thing. And this is the bound, which is an analog of the Gilbert-Warshamov bound in coding theory. Have we lost this permanently? Because otherwise I would suggest to group toward this part of the room. Yeah, I know. All right, good. So how do we do random codes? What is random if we require locality? So we need those local parity checks. Well, we do what suggests itself. We impose locality in the parity matrix and take the bottom part of the matrix randomly. So that's an ensemble of random LRC codes. And we can estimate from above the probability of the distance below a certain quantity, and that's how the Gilbert-Warshamov bound comes about. This is a work of Vivek Kadambe and Arya, and also with Zach and Alexei Frolov a few years back, so this GV-type bound. Is that the best? Can we beat the GV bound? Well, in standard coding theory, at least for codes over small alphabet, we cannot. But for codes over large alphabet, it has been known since 1981 that GV bound can be improved if we go to algebraic curves. And something similar happens for LRC codes. So this is the GV bound. The alphabet, as I said, has to be large. And this is the improvement of GV bound using codes on curves. So this develops in parallel to standard results in coding theory before locality came about. And there is more on that in the work of Abhishek Agarwal and co-authors, which is from last year. So you can now start looking at bounds instead of looking at codes. It is always easier to look at numbers than at real objects, because who knows if the objects exist? You still can argue about the numbers, right? So bounds is an easier path to follow compared to the constructions. Extensions. So there are a few extensions here. And let me discuss some of them in the remaining time. Availability. So what is availability? Imagine that some data on Twitter is sought after by many people. Many. But then one drive is lost. So the first 100 customers are served by the system, but the second have to wait because the processor capacity has been overwhelmed by the demand. And the third 100 has to wait, and so on and so forth. Maybe Twitter even crashes because of that. So to keep Twitter alive, let us try to have many repair groups for one coordinate. And ideally, those repair groups have to be non-overlapping. So if we can recover one lost drive from non-overlapping groups of locations, that is the availability property. So that is the term hot data comes from distributed storage design. So this is the lost coordinate. This is the lost coordinate. This is one repair group. This is another repair group. I want to stress those repair groups do not have to be of the same size. That's whatever the construction comes up, we will live with that. A code is called LRC with availability 2 if every coordinate has two disjoint recovering sets of size R1 and R2. All right, so going back to our interpolation, we interpolate a low-degree polynomial through this set of points and through that set of points. And those low-degree curves intersect only on the lost coordinate. And thereby, we come up with codes with availability. Is that possible? Well, yes. Once we have the idea, here is an example. I will not go through all the details, but to give you an idea, right? So let us say the field is of how many elements? 13, right? So we break 12 into 3 groups of size 4 and 4 groups of size 3. And let us say 1 is lost. Then we can recover 1 from 5, 12, and 8, or from 3 and 9. So we can serve twice as many customers as before, because we have non-overlapping repair groups. And this is the details of the calculation. Interpolating two different low-degree polynomials, delta 1 and delta 2, delta 1 and delta 2, through the non-overlapping repair groups. All right? Well, product codes, of course, will give us availability, if you know what it means. Codes and bipartite graphs will give availability. Direct sum codes will give availability. So there are some approaches motivated by classic directions in coding theory. What about the bounds? The question of bounds for codes with availability is a tricky one and a very much open one. This is one of the first bounds on the rate, a bound on the distance. So this is from the work with Zach a couple of years back. This is another bound, which is sometimes tighter than this one. There is more on the bounds, more recent bounds. Maybe, these two are in general location. This is tightening, I think, for linear codes, Balaji Kumar. But overall, the question of the best attainable rate for codes with availability even 2 is an open problem. We know very little about the distance. This is the bound, and more or less, it's not exactly the end, but that's not far from the end. We don't know if codes that attain that bound exist in general. Tighter bounds are available for availability 2 and 3. Balaji Kumar, the cited paper. So these are the formulas. And the bounds that are related to multiplicities in general, including availability, we could think of this as providing some functionality in more than one way. They are typically tied to questions in graph theory or even metroid theory. And indeed, bounds on distance of codes with availability, at least some of them are derived based on expander graph arguments. But this is only the beginning, because there have been more work on metroids for codes with availability and for LRC codes in general. And so this is a direction if you are combinatorially inclined, and like we're working with graphs and metroids, you can look at these questions, which again are open to a large extent. Well, here is a simple extension. We said correct one erasure. What if we want to correct two? It is still far from the overall correcting capacity of the code, but maybe it is good to be able to correct two erasures locally. Here is a version of the bound on the distance. And the Reed-Solomon-like construction can be extended to meet this bound with equality. It does not require significant new ideas, but at least I want to announce this direction as a possible extension of the basic LRC question, correcting more than one erasure. Hierarchical locality. It's again a new topic, little new topic. What time am I supposed to stop? I see. Oh. Well, I'm wondering if that's happening in another direction and we will need a longer break. I've been skipping some of the slides in thinking that I'm going over time, but let's see how this develops. Hierarchical locality. Let us think of the following. Suppose that more often than not, we would like to correct one erasure. Okay, we know what to do. Suppose that sometimes we want to correct two. Well, the original construction didn't make provisions for that. It said, well, you need to correct more, you go to the global decoding procedure, go to the entire code. How so? We just mentioned that we can correct more erasures. Yes, we can. We can immediately make provisions for correcting two erasures. But that does not take care of the little case of correcting one erasure. So we will have paid more in terms of the parameters than needed to correct a single erasure. What if we combine the functionalities? That is hierarchical locality. Namely, let us say there is a code. This is a code word. Let us say that this blue-colored code is designed to correct some number of erasures, 2, 3, 4, but more than one. That we know how to do. Let us say at the same time that blue code has the LRC property, namely, a single erasure can be corrected by looking at the subset of the coordinates in the blue code. That's hierarchy, right? Correcting 2 and 1 as needed, going to different functionalities of the same code. And you can immediately envision that you can do that for any number of levels of hierarchy. Right? 3, 4, 5, as many as you want. Notation becomes cumbersome, but the idea is abundantly transparent, what we want to do. If you want to write this notationally, you will fill pages. But that doesn't matter, because we already know what we are doing. So every coordinate in the code CI, which corrects several erasures, so the distance of CI is row 1, but every coordinate is contained in a code that is LRC itself. And that is the definition by Biranjit Sasitharan and co-authors, again from Bangalore, a few years back, the ISIT 2015. The Gopalan et al. Bound can be extended by the same argument, no miracles there. So we pay more, of course, for that. We retract more from the Reed-Solomon distance. But that's what we have to do if we want hierarchy. Optimal Reed-Solomon codes are possible. Reed-Solomon type codes, optimal meaning that bound with equality. There is an interesting question here. If the code is such that its global distance is optimal, Are the middle codes themselves necessarily optimal? I don't know. Open question to me. In constructions, it is the optimal codes do have optimal middle codes. Generally, most likely it's not the case, but that is unresolved. We can go to Reed-Solomon-like codes. We can go to codes on algebraic curves. And particularly, I don't want to discuss that in much of detail because most likely algebraic curves are not familiar to most in the audience. But it turns out that algebraic curves are kind of tailor-made for these LRC applications. So algebraic geometry codes have been around for close to 40 years. And they had not found a single application so far before the LRC business. So that's indeed a very nice development for that area because it shows that an idea, however esoteric it may seem, it may come up in very different contexts. So don't give up on esoteric ideas. Who knows how this develops? Nobody knew that would play out very nicely. Why does it work well for algebraic curves? Let me say a little something. So what's an algebraic curve? As we said, it's, let's say, pairs of points that satisfy that equation, x cubed plus x equals y squared. Or generally a tuple of elements of the field that satisfy a bunch of algebraic equations. If there are algebraic geometers in the room, they will call me to a duel tomorrow morning because that's a very crude description of algebraic curves. It's not that what it is, but in practical terms, it's not that far. So it turns out that most good algebraic curves are constructed as follows. So we have those 27 points. And they're constructed as covers of other curves. So we take a finite field, FQ. Well, if you want to be rigorous, we take a projective line. We take another projective line. We take what they call their fiber product. And out comes a Hermitian curves, a set of points satisfying that equation. And that situation persists. It turns out that many, if not most, curves with many points are constructed in that way. But that is LRC because this is one set of repair groups. This is another set of repair groups. Not only is this LRC with availability. So if you want to look at those examples, there have been quite a few papers on that. I think it's, yes?
Are you saying that algebraic codes that say achieve the TBZ bound?
Yes.
Those have optimality properties in the RSS or?
Okay. Algebraic codes that achieve the TVZ bound are asymptotic families of codes. Asymptotics is not a part of this picture, apart from that random thing which I showed. Those codes are constructed in the same way as the TVZ codes. They are below TVZ because of locality, but they are where they are. Is that optimal or not? I have no clue.
So we cannot achieve the TVZ bound?
Of course we cannot.
Even in the asymptotic sense, under locality, we cannot achieve it. Is that?
Yes, this is quite correct. Well, let me retract. The natural way, standard analogy of going to the TVZ bound will not take us there. Is there another way?
So besides Reed-Solomon codes, are there any other family of algebraic that we knew from before that were optimal in some sense that that have good LRs?
Well, optimal in some sense, I probably should repeat the question. Are there families apart from Reed-Solomon families? Are there other families of algebraic codes that were known to be good in some sense, that are also good as LRC codes? And the answer is rather yes than no, as long as we don't insist on precise definitions of being good here and there. But the simplex codes, for instance, that I showed have optimal locality. There are other binary codes with optimal locality. There are good binary codes on Platonic graphs are good, that I mentioned briefly. There is a very nice study of cyclic codes with locality, a line of work. And I will mention this very briefly. But it is, if you are in that direction, looking at cyclic codes is a nice thing to do, because that is very much unfinished. Let me move forward. This TVZ business we can discuss in more detail if you want during the break. All right, good. Maximally recoverable codes, a very open direction of research. So MDS codes are good. We know that from our life experience. Any K symbols can be used to recover the data. Reed-Solomon codes, any K tuple gives us back the data. LRC codes are not MDS. Why? Well, because if K symbols cover a repair group, then they cannot be independent. A repair group implies dependency, instills it, right? And therefore, they cannot be MDS. And then a natural idea that researchers have followed, well, they are not MDS. Please make it as MDS as possible under the circumstances. What does that mean? That means that if a K tuple does not cover a repair group, then it is full rank. So any K tuple that is not dependent because of locality is required to be independent. Right? They are called maximally recoverable. This is not a precise definition. No, this is a precise definition, but it's not the most general definition of MR codes. The first paper is that by, again, the Microsoft group. Here, 2 papers. So this is the one that isolated the concept of MR codes. So if rephrase the definition, a subset of coordinates of size at least k does not contain a local constraint, then the restriction of the code to that subset is MDS. That is MR codes. You can prove that they exist, but the field size is exponential in N, and that is unsatisfactory. Constructing MR codes over small fields is a vibrant, developing, open direction of research. It's a difficult open problem, but it is an open problem. All right? Oh, partial MDS. Partial MDS is the same concept, but it comes from distributed, linked to distributed storage applications and array structures that are attuned to RAID architectures. They impose specific ways of constructing MR codes, and that has been championed by Mario Blum and co-authors for a good number of years now. All right. MR codes are optimal, and the proof is really not difficult. It requires a little discussion that is connected to the proof of the Gopalan bound. I didn't do the proof. Maybe I don't do this discussion here. But the picture, the outcome is this. LRC codes, optimal LRC, largest distance, MR codes. Optimal LRC can be constructed. Can MR be constructed? Not so clear over small fields. Are MR optimal? Well, no. There are examples that show that the inclusion is a proper one. So this is a proper, the yellow is a proper subset of the red. Constructions through linearized polynomials. But the field size, once you go to linearized polynomials, rank distance codes, Gabby-Doolin type codes, then the field size is immediately exponential. While the constructions are nice, transparent, they don't quite rise up to the challenge. The best current result is in this paper cited at the bottom of the slide. There is an exponential decrease of the size of the field, but the size is still exponential. All right. Again, a variation of linearized Reed-Solomon codes, but a nice work overall. This is already recent, less than a year back. All right. What about the maximum length of optimal LRC codes? Why are we asking this? Well, again, a code is called optimal LRC if the distance is this, satisfies the Gopalan et al. Bound. So let's say we give up locality. Let's say R equal to K, so it is a Reed-Solomon situation. Every code has locality K. As I said, well, this is kind of clear. The distance is at most n minus k plus 1. The code is MDS. So how long can be MDS code? This is a hugely famous open problem, a sort of Fermat's last theorem of coding theory, of projective geometry in general. The latest advance is by Simeon Ball, 2012, but the problem is unresolved. I don't advise to look at that because that's a hugely difficult question. So it would be natural to assume that since this is a singleton type bound, the distance of optimal LRC codes would be also constrained. The length of the optimal LRC codes would be also constrained. How long can be optimal codes? Well, there are some answers now. Very nice. With locality, the length, this is the work by Venkat Guruswami and co-authors, which came out this year. So if the distance is at least 5, then the length is at most q to the 4. This is not final. It is more of an artifact, this bound, than a definitive answer. Why? Well, because the proof has utilized a particular structure. It is not at all clear to me that that structure is this structure that should enter this argument. So I would say this is not a final result, but nevertheless, it's very nice. There are optimal codes of distance 3 and 4 of unbounded length. So this is sharp. Unbounded length, distance up to 4, q to the 4, distance 5 or more. There are codes of length q square for distances 5 and 6. And very recently, with Zitan Chen, we did something on codes with hierarchy. Again, optimal cyclic codes with hierarchy of unbounded length. Other than that, it is open. Are there codes of length q to the 4? I don't know. Are there codes of distance, not 5 and 6, but let's say 7 or 8 or 9 or 10, of length more than q? It's unclear. Sequential repair, that is another variation. So what is sequential repair? Let's say there are 2 erasures. We repair one of them by going to some repair group. Now we have repaired that one. So we use another repair group that includes the recently recovered erasure and repair the second erasure, and so on. So sequential relies on the already obtained result in repairing further erasures, all in a local way. Here are references, and I will not say more about that. Parallel. Well, parallel is same as sequential, but the repaired symbols are not used to recover subsequent erasures. Again, there are works on that. Cooperative repair. I think the first paper of that was yours, Arya, right? On cooperative. Yes. Yes, so Arya and Ankit have introduced this problem. And the reason for this reference that came up 2 days ago is that it was shown that cooperative repair is equivalent to one version of the private information retrieval question. Single server PIR with side information is exactly the same as cooperative repair. This is not very surprising, because if you are familiar with private information retrieval PIR, then locality immediately comes to mind. and that one version of that problem is equivalent to one version of the LRC problem, it should have been expected. But here is the result. I invite you again to look at Erasure coding for distributed storage, this overview from last year. It already misses the latest results, but it contains a large part of the results obtained by up to that time. These are two. So this is a plot, again, a picture from their paper. So what did we do? What have we done by now? LRC codes, we did single erasure, yes, multiple, yes, sequential, cooperative, hierarchical, parallel, availability. All of those have been mentioned. And there are more that didn't fit that scheme, but were also mentioned just now. Let me switch to another problem. Well, you would say, I favor Arya's work because he's here. No, I favor this work because it is good work. And because I think it is relevant to this question, and that is LRC codes on graphs. In general, Arya came up with one version of that question. There was another work with Alex Demakis, his student, Shanmugam, I forgot the first name, unfortunately. And there was an equivalent discussion before that, before this distributed storage had games, the guessing games on graphs, entered the literature in about 2005, 2007, maybe slightly earlier. So what is a graph? Not in general. In general, we know what's a graph, but what is LRC on graph? So previously, we have done the repair, assuming that we can go to any subset of coordinates. Well, let us say we cannot. Let us say we can only communicate with those that are imposed by a particular graph. So not only communication constraints in terms of the repair degree, but also connectivity constraints. The underlying idea. So let us say there are three nodes in memory. Those are, well, you have not seen this in your lives, but these are called floppy drives. They existed before CDs, and CDs existed before cloud. So that's what people used. I make a bet. Nobody can tell me how much information one of them carried. Yes. That's correct. I recently threw away my last batch. Right. So let us say this is a recovery graph. What does this mean? This means that 1 can be repaired from 2, 2 can be repaired from 1 and 3 can be repaired from 1. So this is the connectivity structure. Let me, if I stand on that side so that you can see, then I go away from the camera. So there are multiple constraints, local ones. Let us see that each node can recover the content from its incoming neighbors. So the recovery sets are 2, and that is for 1, 1 and 3, and that is for 2, and 1, this is for 3. And the question is how much data can be stored on such a graph under these constraints, right? This is as natural a question as it can be. And which coding scheme achieves the limit? So the question of storage capacity, the network is defined by a directed graph, VE. There are n vertices and a set E of edges. Each node stores a symbol from FQ. And a storage code is a set of vectors of length n. So each coordinate of the vector assigns a symbol to a vertex in the graph, one vertex. There are recovery functions that do the recovery according to the graph. Going back to the example of the previous page, that's on the previous page, that's what they do. The capacity, storage capacity is as defined, is the maximum size of the code that fits the recovery functions. That is a storage code for this graph. So what's log Q of that code? A difficult question in general. There are some answers, but overall it is very much unknown. At most n, of course, but we will say a bit more. So the storage capacity should not depend on the field. So we define sub-Q of capacity, the best realization over a finite field. And well, it is clear that we can do this, that the limit exists, and it is equal to the supremum. And that is because of the additivity of this capacity. It is subadditive, and Feket's lemma applies, and Feket's lemma says exactly that for subadditive functions, the limit exists, and it equals to the supremum. So the question, the definition can be taken lim of capacity over a field Q as Q goes to infinity. Let's look at an example. So here's a graph. It's as simple as it can be. Each node stores a single bit, 2 bits, and we can store 2 bits. So the capacity of the field of 2 elements is 2, B1, B2, B1 plus B2. So the capacity is sub Q, and it is 2. Well, that was an easy example. Here is a difficult example. A pentagon, right? So, and this is a storage code for the pentagon. It's completely not obvious that it's a storage code. And the recovery functions take a while to design. For instance, in each of the code words, x1 is x2 and x5. The functions are non-linear, obviously. Well, maybe not obviously, but they should be non-linear to attain capacity. So this is the set of recovery functions. And therefore, the capacity is at least log 5 base 2. Capacity over the field of 2 elements can be shown to be log 5 base 2. Is that capacity? Well, no, it's not. Capacity is in fact higher. It is attained over 4, over the field of 4, and it is 2.5. And that's already a separate paper, right? With this reference here. So you can see that this opens possibilities for research. In fact, a large number of open questions. You tell me. No? Oh, the reference is no, it's not, no. So this is, in fact, 2011 and 2013. This is Kleinberg, Lubetsky.
Oh, yeah.
Is that right?
Yes.
All right, good. It is not so difficult to convince yourselves that the capacity of a graph is sandwiched between max matching and the vertex cover. Both are easy to understand, and the gap between the two, so max matching, right, they are known concepts. What is a matching in a graph? A matching is a set of edges that are disjoint in a graph. So that's a matching. One edge is a matching. Maybe we can fit 2 edges. What's the maximum matching? That is the lower bound. How did I manage to get there? So max matching is at least a lower bound on the storage capacity. That is clear by the definition. The vertex cover is also clear. What's the vertex cover? Well, there's a graph. And a vertex cover is a set of vertices that covers all the edges. So I now refer you to the latest work on this, where there are approximations for storage capacity of planar graphs, cycles with chords, but generally figuring out storage capacity of a graph is a difficult question. There is a work on duality. So even the first papers on storage capacity mention duality between storage capacity and index coding with site information. In the index coding is a famous question in latest one of the latest trends in information theory, where you propagate information from a broadcaster to a set of nodes, each of which carries some side information about the targeted quantities. And it has been shown that one capacity, index coding capacity, and storage capacity determine each other. You know one, you know one, you know the other. Well, a bound on one gives a bound on the other. That is also clear from the equality. A large group of open problems here. And this finishes my locality discussion. So as you see, a repair degree is a really very fruitful question. Gave rise to a range of new problems, many of which are open. And it led to many very nice works within computer science and information theory communities. And in the second part, we will look at repair bandwidth and associated questions. And you will see that it is also an equally rich, if not a richer part of the coding for distributed storage. So this will wrap up the first part, and we'll meet after the break for the second part. All right, let's move on slowly. And again, the main message, I hope to have convinced you to some extent that, see, now I'm drawn to this screen to stay closer to here. If you can turn the recording, then I may be here. All right? And how about here? Is that? No? No? Okay. All right, thanks. So then it returned to a normal setting. The next step would be to discard this screen and start writing on the board. That would be even nicer, but okay. So I hope that I have convinced you to some extent that there is a range of problems that had not been anticipated, that are new, that are interesting, that are worth looking at and studying. And that is the idea behind this presentation. And with that, we should like to move forward and discuss the repair bandwidth. Previously, the question was, how many nodes do we have to talk to recover a single erasure? Now the question is not as much that, but how much information do we need to carry to cover a single erasure? What is carry? In the standard coding problem, this question does not arise. We don't particularly carry information anywhere. We take the available part of the code word, recover the information, and that's it. There is no function of moving it anywhere. It is not a constraint, but distributed storage precisely injects such a question. Move the information to the failed node to complete the repair. So looking slightly more broadly, there is a task. There are two tasks in coding for storage. One is providing the picture sought by the user, the information, that is data collection. So from every node, we carry L symbols of let's say, a finite field. And there is a question of node repair, the task of node repair, where this node is knocked off. And there is a repair center that connects to, the notation will be D will be the number of helper nodes now. So D is not the distance anymore. The distance does not play a role in these questions. I'm sorry for this change of notation. That is a psychological effort to make. But D will be the number of helper nodes. All right? So, and they transmit the information to the repair center that creates a replacement node. So there are two tasks, data collection and node repair. A fundamental contribution of the Dimakis, Godfrey, Wu, Wainwright, and Ramchandran's paper was to to formulate the concept of the information flow graph. This is new. This is really a fundamental contribution. It was very helpful. It is at the start of all the discussions related to the repair bandwidth problem, regenerating codes, and a range of accompanying questions. So we look at the nodes, and they communicate some amount of information to create a replacement node, and those replacement nodes are being created until the task of the data recovery, and then this set of active nodes transmits the information to the data collector, who provides the data to the user. A rough description of the information flow graph, but a very useful outcome out of this consideration, not a difficult one, by the way, but this is a new viewpoint that was really the contribution of that paper. Yeah, before saying that, let me fix the notation for this slide at least. So we walk away from this idea of coding theory as such, so that there are k data symbols that are encoded, and we formulate this slightly differently. So there is a set of data. The word of the day is a file. A file of size B is encoded into n nodes. So we take information, spread it around n nodes in storage. Each node has size L. So we store L symbols of the field on the node. K nodes suffice to recover the data. K may be related to the dimension of the code, maybe not. In general, it will be throughout most of my presentation, but in general setting, it is simply that K nodes suffice. Maybe it is the dimension of the code, maybe not. D helper nodes are used to repair a failed node. A helper node contributes beta I symbols for node repair. All right. So the cut-set bound, which imported the ideas of network coding into this regenerating coding problem, says that the size of the maximum capacity of storage is bounded above by the quantity as shown here. L is the size of the node, D is the number of helpers, beta I is the repair bandwidth of node I, the number of symbols that the node contributes. So the ideas of network coding proved fruitful for this regenerating code problem. And there are two versions. So there is a curve, there is a whole curve, which relates to the trade-off between B and K. There is a minimum storage point, MSR codes, minimum storage regenerating codes, where the size of the node is B divided by K, and as we will see, this is the case of MDS codes. And there is minimum bandwidth codes, where the relations between B and K are as shown here. So there are 2 points. Again, the 2 points are from their paper. And there is a whole trade-off curve of intermediate points between these two. We say that a code NKL, so N is the length, K is, for the time being, the number of nodes that are required to recover the data. L is the size of the node, has optimal repair property if the repair bandwidth meets the cut-set bound with equality. We want to optimize. Apart from the repair bandwidth, we want to have the field size as small as possible, the size of the node as small as possible. Optimize Q and L for the ease of implementation. Somewhat on a more general level before moving to the concrete results. The repair problem is one of the first steps of moving the coding question and the question of representing information in general to the network and to network environment. I feel that this is a timely extension of the questions that we have been considering in information theory so far. You might say, we know multi-terminal information theory, that is correct, but multi-terminal relates to very specific models of networks, and multi-terminal mostly looks at noisy links between those nodes, interference channel, broadcast channel, relay channel, and so forth. Here we look at more general classes of networks, maybe with topology constraints, but general classes rather than individual examples. And here we don't focus as much on the noisy links as on different kinds of recovery tasks that arise, for instance, in storage. So the question, how can information can be stored and recovered in networks, I believe is one of the currently active research directions in information theory in the large and in computer science at the same time. Network coding is the first example. That's a limited version of the question. There is a source and there are destinations, and we carry the information from a multicast problem, for instance, from the source to the destinations. But there is a vast range of questions of a similar kind, some of which I will mention, so multiple research directions arise. So apart from the specific questions that I'm going to discuss, I would like you to keep in mind this idea, general idea of representing information. Going back to the question discussed in the beginning of the second part, regenerating codes. CI. So what is CI? The notation for the entire part of the presentation will be, oh yeah, here. The code encoding will be as follows. C capital C1, C2, Cn is a encoding or code word. Every coordinate is L symbols over some finite field. So L is the size of the node, or well, that's it, right? L symbols over a finite field. And that is for every coordinate. Node size, also known as sub-packetization. That is from more of a network type terminology. We take a node and we quote unquote sub-packetize it. We break the packets into little chunks, represented as those rectangles in the picture, and so sub-packetization is the same as the size of the node. So Ci is the ith coordinate, and that's a function of the information acquired from the coordinate Cj within the set of the helper nodes. So R here is the set of the helper nodes. The number of helper nodes is D, and that is at least K. D number of helper nodes greater or equal than K. I will say a bit more about D as we move forward. So there are functions that take the data on the jth node, move them to the repair center, and jointly that data can be used to recover the failed node Ci. So the failed node, the helper node's repair degree, downloaded information, and that is a representation of my code word. Here, node 1, node Cn, one node is erased, and the task is to recover that node. From now on, we go from the general setting of the cut set bound. Here, we go to what they call the MSR case. MSR case, this is the one corner of this cut set curve, cut set bound curve. Every coordinate is an L-dimensional vector again over F. And we call them NKL MDS array codes. MDS code again has the same meaning. So MDS code as before. MDS encodes K into N symbols, N coordinates, N nodes. Better to say N, K nodes into N nodes. Let's keep the terminology. every k nodes suffice to recover the file, all the information. So that's the MDS property. So we do not stress the distance anymore of the code. MDS is now that every k recover the entire file. K data nodes, n minus k parity nodes, contents of any R nodes can be determined by the other k nodes. All right? The value of L is called sub-packetization. C is called a linear array code or a vector code. So there is a difference between array codes and vector codes and scalar codes. We look at that picture. So that code there, every coordinate is L symbols of a field F. That code is not necessarily linear over the extension F to the L. It is F linear, but the coordinates themselves, they cannot be multiplied and be still expected to be preserved in the code. So they work as vectors over the field, but not necessarily linear over the extension field. So a linear vector code is F linear. If it is linear over F to the L, then it is called a scalar code. So Ritz-Solomon codes would be scalar codes, right? They are linear over the big field, whatever that is. But array codes in general, they are only F linear. MSR codes are necessarily MDS codes. So if the codes are on the MSR part of the trade-off of the cut set curve, then they must be MDS by definition. Just take this as a part of the definition. Let's not discuss why that is true. So this injects a bit more terminology than previously. That terminology, at least if you have not seen this before, is somewhat unusual. What is important to remember is this representation. This representation of the code, C1, C2, Cn, over a field. So every coordinate is an L vector. It is an MDS code. Let us now prove directly a version this cut set bound for the MDS case. This could in principle be the starting point of this presentation. So what was said before is important for setting the problem, for the history of the question, but this could be a starting point. The remark is as follows. There is a code of this form here. There is a code of this form. L, N, K. So L is the number of rows, N is the number of columns, K is what is set here, encodes K nodes into N nodes. The question is, what is the minimum number of symbols of the field F that need to be transmitted to correct one erasure? The same question in this vector setting. Answer. The minimum number is, by contacting D helper nodes. Answer, DL divided by D minus K plus 1. We will give a proof momentarily. But before doing so, let us consider this expression. So let us say that we look at K nodes. The code is MDS. K gives us everything. So look at K nodes. K. And then we have DL divided by K minus K plus 1. So the number of downloaded symbols is DL. No surprises. KL, I should say, right? Because K is D. Is equal to KL. Not surprising. But let us say we are allowed to contact K plus 1 coordinates. So what do we have? K plus 1L divided by 2. By plus, right? Time. Sorry. K plus 1 times L. So let us pretend that k is the same as k plus 1. That is not as much of a stretch. So we have, in fact, managed to correct one erasure by transmitting a half of the symbols compared to contacting k nodes. That is a stunning development, right? We can look at fewer, download a smaller amount of symbols. This is a decreasing function of d, this right-hand side of the cut-set bound. And so the minimum is attained when d is n minus 1. All of the nodes that are still available, and that is the smallest. So the observation is, we are allowed to look at all the coordinates of the code word, but overall we carry much less information than looking at k coordinates. It's not something we knew before this work. All right? So this is the, let's prove this. The proof goes as follows. The code is MDS. So what does that mean? That k, any k gives the full information about the code word. So k minus 1 give no information about the erased node. To learn the erased node, we would need the case symbol. So from k minus 1, we learn nothing. Well, from k minus 1, we learn nothing. Therefore, from any d minus k plus 1, we should gain the L symbols of the erased node. From the remaining within the helper set, right? K minus 1 do not give anything. So everything is given by the remaining. All right, so let R be a set of helper nodes of size d. Let I be a subset of size k minus 1. So what we are being told that downloading the symbols from the complement of the set of k minus 1, we gain at least L symbols. Yeah? When I say what? I'm sorry?
The first condition that sees MDS, if and only no k minus 1 will carry any information, is that in the worst case?
What is the worst as opposed to? There is no worst. This is the definition. This is the definition.
If I have a systematic
Systematic or not, no k minus 1 will give you any information about any other coordinate. This is the information theoretic argument. Simply the entropy of the node will not decrease, conditional on what is provided in the k minus 1.
There exists such a node, but there may, you might also have like one node that depends on fewer than k minus 1.
MDS,
Yeah, the minimum distance in that case would be lower, but your
MDS does not happen. This is the definition of an MDS code. You are quite right. Yeah, well, that's what Ari is saying. You see, this is not a theorem. This is the definition. See? This is proof by authority. Okay, good. So the sum of the beta i's, over the complement is at least L. Well, let us summon all the choices of I, the set of k minus 1. On the left, we inject another sum. So how many choices of k minus 1? There are d choose k minus 1. So on the right, we multiply by this thing, the binomial coefficient. So let us interchange the order of summation here. Interpose these two sums here on the left. We get this formula here. We summon all the coordinates within the helper set. We summon all i's of size k minus 1 such that I is inside, little I, the coordinate, is inside that set. How many sets of that kind are there? D minus 1 choose k minus 1. Summon I remains, beta I. On the right, we still have this binomial coefficient. Divide this by this, and the cut-set bound comes out, right? So this is a proof. So MDS gives you the MSR point immediately with no additional arguments. So this is a very interesting quantity, a basic thing in coding theory. How much information do you need to move to correct one erasure in an MDS code? By contacting D coordinates. Answer on the right. Or one might say that's the lower bound. Can we do this? Jumping ahead, the answer yes. There exist codes that do that. All right. So the repair problem again for the MDS codes now. there is one erased coordinate. We contact d coordinates and transmit some information. Maybe not the contents of the nodes. Maybe we transmit some function of the contents of the nodes to recover one erasure. A formal definition of the repair problem, I will throw in notation, but I will not say anything new. A code word where each coordinate is an L vector over field B. It was F, it's now B, I'm sorry for that. A node can be repaired from a subset of D helper nodes Ri by downloading beta I symbols of B if there are functions Fij that take the helper nodes, make it B to the power beta ij, so that is the symbols that are transmitted from j into I, and the function that takes all of those symbols and outputs the lost node, the contents of the lost node. Well, this is the function gi, takes the downloaded information, and the sum of beta ij's is beta I. Right, so that is repair. The repair bandwidth is the minimum of the transmitted information. A general definition of the repair question. And as we already said, that repair bandwidth satisfies the cut-set bound. So this slide does not add anything to the intuitive discussion already made on the previous slides. Of course, we want to construct optimal bandwidth codes. That is our task. Product matrix codes were the first construction, restricted to low rate, but they were the optimal repair codes. Rashmi Shah Kumar, a sequence of papers, and also Changdo Su and Kanan Ramchandran provided constructions with this limitation, so low rate. That was a nice advance. At the same time, in storage, probably or arguably, high rate is better because we don't need that many parities. One would not need a large protection because we are correcting one erasure, two erasures, but for that, not many parities are needed, and few parities means high rate, so high rate would be preferable. So the task of high rate is still at hand, or any rate. For any case, there were existence proofs in a sequence of works, and then there was a construction for any parameters, including high rate, and that construction I'm going to discuss in slightly more detail because it is also somewhat related to this Reed-Solomon construction discussed previously. Not exactly, but there will be many commonalities. So we are constructing NK MDS codes with optimal repair. What is sub-packetization? Sub-packetization is R to the n, R being the number of parities. Let us put this on the board. R is n minus k, the number of parities. So sub-packetization is R to the n. Sorry, yeah, I'm making you to turn this thing all the time. R is n minus k. We begin with d equal to n minus 1. So we contact all the surviving nodes. I will present this construction. This construction can be extended into codes with universal repair, namely, let us say we want to contact, as we said, the cut-set bound is a falling function of the number of the helper nodes. Maybe in some situations we want to contact n minus 1 nodes, in some situations n minus 2, in some situations we want to go as low as k plus 1 nodes. Is it possible to have a construction with universal repair? Give me the number of helper nodes, I perform the repair. Yes, it is possible. So this is universality. And instead of n minus k to the n, the sub-packetization now, L is d plus 1 minus k to the n. I don't know what this means, by the way. What is d? Because this is for any d. No, there's something wrong here. I'm sorry. This is probably, this should be R to the n. I'm not sure what is happening. This last line is a mistake. It is also possible to repair more than one erasure. Again, within the same framework, the largest number of erasures that we can repair is the number of parities, right? Because if R symbols are erased, we are still left with K symbols that will give the entire code word. So R erasures can still be repaired. Let us say there are H erasures. It is possible to construct codes that repair any H erasures from any D helper nodes from K to n minus H. Sub-packetization is S to the n, where S is LCM of 1 to R. This is correct. Something like this is here, I just don't remember. Over the field F of size at least Sn. So the field size is still is more or less linear in n. Sub-packetization is exponential in n. And this is work with Min-Ye from 2017. I will go over this construction. A few elements here should be mentioned. You might say, well, you say that the field is small, but every column there, every vector is of exponential length. Is that a cheating of sorts? You moved the size of the field into the length of the column, and you are now saying that the field is small, but the sub-packetization is exponential. Yes and no. I will show to you that exponential sub-packetization is necessary in these problems. You cannot do optimal repair if you do not allow yourself exponentially long columns. At the same time, small field is still a boon here, because what they did previously, they had both exponential field and exponential sub-packetization. So at least this is as much as we can gain, hope to gain in this problem. All right. So all the details aside, let us look at the basic question. We want to repair one erased coordinates from D helper coordinates. The code is MDS. Any K give us the entire file. The code is formed of L by N matrices over F. A matrix encodes KL symbols of the field F into NL symbols of the encoding. So think distributed storage. We put L on a storage node. 1 is erased. Our task is to repair. I guess this question should be clear. We define the code in terms of parity check equations. Each node is an L vector over F. So our multipliers here, our coefficients, should themselves be matrices over F. So this is a general parity check equation. The code is F linear, so everything is in place. The parity check equations in the matrix form are as shown. Each A is an L by L matrix over the field. There are R parities, and all of this should be 0. So the question is to construct an optimal repair code with these parities. What we shall do, we will follow the Reed-Solomon intuition. We will construct this Bloch-Vandermonde structure, and it remains to define the matrices. Why Vandermonde? Well, because that's what Reed-Solomon codes have in this scalar case. So this is the first thing to try if you try to extend this to matrices. And if you are able to figure out what the A's should be for optimal repair, then the construction is in place. I'm sure you know this, but this Vandermonde business works not necessarily over a field. Over the ring of matrices, the Vandermonde machinery is still in place. In particular, the matrix is non-singular, as it is in the scalar case. And that is a big help in this task. All right? So what are A's to give us a good code? Looking at the literature, we isolate the properties that are required for optimal repair. They should be commutative. They should commute these matrices. This is not necessary, but this is sufficient. the differences should be invertible. That is an unusual condition, right? Because differences of the matrices is not something that is easy to think about. So which matrices are such that their differences are invertible? Well, I cannot think of anything else but diagonal matrices. So we shall take diagonal matrices for that. And then everything will be in place. So we just need the differences to be invertible. We need as many non-zero elements in the field as there are, as the total length of the diagonals. And that will be a natural restriction. So we take our matrices in the following form. Sorry. EA is the standard basis vector, so that's a fancy way to write a diagonal matrix with lambdas on the diagonal, right? We have the basis vector, we have the basis vector, we do this outer product of the vectors, we get a matrix with 1, 1, and at that position we write the lambda. All right? And the lambdas are distinct elements of the field. And what is important here, we use the expansion of the label of the coordinate to the base R the number of parities. So that labeling is crucial in the repair task. That is really the new idea injected in that work, introduced in that work. The code word will have the form as before, and the code word will satisfy those parity checks. Right? So it's as simple as it can get. Multiply by diagonal matrices, say that the product is 0, take that linear code, that will do optimal repair. The idea underlying this construction, every row forms an RS code with different evaluation points. And the evaluation points for the 8th row are given by the expansion of the label of the row to the base, which equals the number of parities. Do that, you get optimal repair. So let Ci be the missing node. We shall repair the contents of the node by groups of size R. And those groups will differ only in the one position of the label. So this is the expansion to the base equal to the number of parities. We shall group the nodes according to the value in one position of the label. So as that label runs from 0 to R minus 1, that's expansion to the base R. We get a group of nodes, and we will repair that group using the set of its parity check equations. I know that it is difficult to follow this, and I invite you to look at this. Just trust me that this system of equations arises. And I will show you what happens as you take this subset of parity checks. You will see that subset of parities, you will be, at least it will be possible to believe that optimal repair is possible. So we write those parities as shown. Remember, the I is the erased node. The other nodes are available in the helper set. And minus 1 nodes. So there are equations of this kind according to the groups of those labels that we isolated. We sum those equations on U. We get this equation for the set of coordinates, which I copied on this page. I write this equation in the matrix form, and the miracle happens. So here we have a subset of the erased node that differs in the ith position of the label, of the row label. This is what we have on the right. So on the right, the matrix that multiplies the downloaded information turns out to be a matrix of rank 1. And so this tells us that to solve for the unknown subset of the erased coordinates, this is van der Monde, right? So this is good. Here, we need to download one symbol out of the jth coordinate. That one symbol is a linear combination of those symbols here on the right. This idea, in fact, is what wireless communication researchers call interference alignment. So we can align the quote-unquote interference from the helper nodes in a way that it is multiplied by a rank 1 matrix. And therefore, we can look at the sum of those symbols from the helper nodes rather than at one symbol. And that saves the repair bandwidth. All right, so we have done that. It remains to convince ourselves that the recovery is optimal. That is a straightforward computation. As I said, for each group, from each of the helper nodes, we get one symbol. So we count the total number of the downloaded symbols. And it exactly fits the cut-set bound. N minus 1 times L divided by R. So we look here, it's something like that. N minus 1 is D now. The bottom part is exactly the number of parities. And that matches the lower bound. So optimal repair is possible. All right. Let me see. Yeah, so interference alignment, van der Monde, Reed-Solomon codes all enter this picture. What about two erasures? For two erasures, there are now several versions of the problem. Namely, it is possible to correct two erasures in one shot. So we download all information to one location, we do some computations, and we repair the failed nodes. Or it is possible to do distributed repair. Namely, we repair the first coordinate at its location, we repair the second coordinate at its location, and maybe the repair group, its centers exchange some information, which counts toward the repair bandwidth. So that is called cooperative repair. Right? So now we have, for two erasures, we have several versions. The centralized repair or the cooperative repair. As I defined the cooperative repair, that involves two communication rounds. Originally, it was defined for more than two. In the first work that discussed cooperative repair, Kenneth Schum and who? I don't remember the first name, 2013. But in work with Min, yeah, we showed that 2 rounds suffice to do optimal repair in the cooperative case. All right. The cut-set bound that we showed for the centralized repair, the code meeting this bound is for the optimal repair, that's already said. And this is a version of the cut-set bound for cooperative repair from that paper. Let me see. Yes, I will say more about this cooperative bound in a few minutes. But for the time being, once we have the idea as described, it is possible to derive versions of that cut-set bound for different versions of the repair question. H is, so here H is the number of erasures that we are correcting. Centralized model, cooperative model. Codes that meet these bounds with equality are said to have H, D optimal repair bandwidth. H is the number of the erasures, D is the number of the helper nodes. Universality, varying number of helpers, the cut-set bound for different Ds. It is possible to perform repair even in the situation when some of the nodes provide incorrect information. So suppose we download, but there are errors. Why are there errors? Well, maybe there are unreliable links. Maybe the node, as they like to say, are Byzantine. So computer science terminology, when they say that there is an error, so they collude against us. They deliberately provide incorrect information. And we still can perform the repair as long as there are not that many adversarial nodes. So all of these versions are in place once we have the basic question. Universally error resilient combination of all of the above. So the varying number of helper nodes, the varying number of erased nodes, error tolerance. So in this work with Min, we looked at all of those situations, and constructions are available as discussed. So secure distributed storage. If you like questions of security, which are currently added to many topics in this direction of information theory, in this strand of information theory. So what is secure? Suppose an adversary wants to learn the contents of the failed node. From observing information from the helper nodes transmitted over public links. A valid question, right? Because they do security for all kinds of problems in applied information theory these days. So listening to the downloaded information, is it possible to recover the contents of the failed node for an eavesdropper? So there is a version of that question, and there is this secure capacity of distributed storage. So that is the maximum number of files that we can store so that the eavesdropper does not learn anything about the contents of the failed node from downloading. So there are recent works. There is a recent work on this, achieving secrecy capacity of MSR codes for all parameters. The foundational work is in 2010. It was right after the original work on regenerating codes, but now this secrecy capacity problem has been resolved constructively. That construction is based on this van der Monde constructions that are discussed, by the way. Yes? H is the number of erasures that we are correcting. So remember, there is the number of helpers, and maybe we want to correct more than one erasure. You are saying that this is a mistake, right?
No, okay, fine. But why did they not use H to denote the number of helpers?
No. We'll discuss that, but this is a mistake. This should be n plus d minus k.
Okay, that should be n.
Yeah, it cannot be H. It cannot be H. Why did they use H for the number of failed nodes and D for the number of helpers? It beats me. I cannot say anything. Yeah, you see, it took me years to overcome this. I don't know why F is not the number of failed and H is not the number of helpers. And D. Yeah. All of this is a slap in the face. All right, very good. So this secrecy capacity question has been recently addressed satisfactorily. What about sub-packetization? I was kind of claiming, without much justification, that exponential is needed. At first, well, not at first, but relatively early, Sri Goparaju, Tsahitamo, and Rob Calderbank had an exponential lower bound on sub-packetization, but exponent is x square root of k. Whereas in the constructions, it is x to the n. So there is a gap, substantial gap, right? It's x to the power n compared to x power root n. In a recent nice advance by Al-Rabi and Guruswami, 2019, this year, they sort of closed the gap, but they went from square root to x to k. Very nice, very nice. But this is a far cry from what we know. So attaining optimal sub-packetization or tightening the bound is a big open question in this business. Is it possible or not? I have no idea. So here is an open question that I invite you to look at if you are inclined so. Repair by transfer. You see, as I said, these questions, they introduce more and more variations. So what did I do in this optimal construction? I said, we look at the entire node, we do some processing, we move that information to the repair center, and well, we move one symbol, but we have looked at all the symbols at the helper node. Maybe this is wasteful. Maybe we should require that what we look at, that we transfer. Right? Repair by transfer, or optimal access. So optimal access is basically download what you read. NKL MSR code with that repair degree. Each of the helper nodes provides that many symbols that would fit the cut set bound. C has optimal repair property. And the symbols provided from the helper nodes are exactly the symbols accessed on those helper nodes. that is optimal access or repair by transfer. That's an additional constraint. So bounds should be tighter. And that is indeed the case. There are constructions with sub-packetization of this form. So this is optimal repair and optimal access codes. There were two papers that were almost concurrent. They work with Min of 2016 and Birenjit, Sasitharan, Maina Vaja, and Vijay Kumar, again the same year. The idea behind that, I will not be able to present the details. This is more cumbersome than the first construction. But we have layers of those independent MDS codes, and then those layers are coupled in a specific way so that the nice repair properties are supported. This coupled lay perspective in particular was promoted in this work of Sasitharan Vaja Kumar, 2016. And then there was a work with Maina and Min, and well, we joined forces, and it was published in this Usenix FAST conference, a conference that targets system designers. So we advertised those coupled layer codes. So clay comes from coupled layer perspective. So with that sub-packetization, there was a concurrent work by Ji Li, Xiao Hu Tang, and Chao Tian that again addressed this coupled lay perspective in the context of transformations to enable optimal access repair in MDS codes. Again, similar to these results. So optimal access is also possible. And a result by Balaji and Kumar says that this sub-packetization is in fact optimal. So this is optimal from all perspectives: optimal bandwidths, optimal access, and the smallest possible sub-packetization. So the optimal access problem is more or less addressed. But codes without optimal access, no, that is open. All right. Very good. So we said, yes?
Quick comment about that bound that you said N and H, they should be replaced.
Yeah.
I think if you put H equal to 1 there, then it shouldn't be actually. It has to be H, because take H equal to 1. You want to retrieve something very similar to
yeah, you're right. You are right. You're right. I confused it. I thought. Yeah, I forgot about D. So D plays the role of N.
Yeah.
I take it back. This is correct. The formula is correct. Thank you. Thank you. Thank you. Thank you. This is as it should be. I thought it was negative for whatever reason. No, it is positive. So D plays the role of N. H is the number of erased guys. You see, I'm still struggling with this notation. Thank you. Good, 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 good. So we said optimal bandwidth, but in information theory, out of many places, or computer science, in fact, approximation algorithms. All right, well, optimal bandwidth is good. Well, what is it if it is not optimal? But not far from that. Is it possible to do better? Yes. It is, in fact, possible to do much better. If you allow yourself epsilon MSR codes, means that the bandwidth is optimal times 1 plus epsilon. Then sub-packetization can be much, much, much smaller. There's a doubly exponential decline. Not exponential, but doubly exponential. It can be log n, as opposed to e to the power n. So epsilon MSR codes are possible. This is a nice idea and nice implementation of this work. Let us briefly talk about cooperative repair. So what is cooperative repair again? We take the two erased coordinates, we take the helper group, they provide some information to the first erased they provide some information to the second erased. So they do some computations. Maybe the information provided in the first round is not enough to repair this guy. Maybe the information provided in the first round is not enough to repair this node. But once they have computed something, they shuffle this information back and forth in the second round. And maybe with what they have received and what they had computed in the first round, they now can figure out their values. So that's the idea of cooperative repair. The first round and then the second round provides the missing components. It is similar to network coding, where we receive A and we receive A plus B by another route, and A plus B together give us B. And this is along the same lines. This idea, general idea, of course, appears in many places. And cooperative repair is one of them. So what do? We say that this is the cut set bound, and this cut set bound provides us the structure. So H is 2 in that picture, right? Each failed node. So this is the formula. We break the formula into 2 components. Each failed node downloads that amount of information from each of the helper nodes, right? DL, H minus D plus K. And then each failed node in the second round downloads this information here, from each of the other nodes in the group of the erased coordinates. So these are the 2 rounds described here in that picture. And the cut set bound suggests the structure of this repair. This is what is done in the constructions to achieve optimal repair bandwidth in the cooperative problem. Instead of reading this theorem, let me tell you what this says. It says that cooperative repair is probably stronger than the centralized repair. Specifically, any optimal repair code in the cooperative model is optimal repair in the centralized model. That structure presented in the previous page suggests that answer, and that is indeed the case. So there is a theorem of that kind. Cooperative is probably stronger than centralized. The general results are as follows. There exists an explicit family of MDS codes that can optimally repair any H from any D, where D is K plus 1 or more. The number erased is for anywhere from 2. This is cooperative, so the smallest number erased is 2, to N minus D. The codes are over any field of size at least D plus 1 minus K times N. So the paper was published this year. It appeared as a preprint maybe a year and a half ago. All right. So let us briefly discuss how this is done. We are going roughly till when? 12, so maybe 30, 40 minutes more. Let me see how much I have here. Yeah, well, this is a slightly more detailed presentation of this cooperative repair. I don't know how useful this will be now, but let me tell you maybe roughly by hand waving how this is happening without discussing all of the details. We set up parity checks using, again, an algebraic approach, distinct elements of the field. And what we do to repair this is only to repair 2 nodes, even though this is generalized, but generalization follows the same idea and uses more elaborate notation. So we provide to the first coordinate, exactly as I said, some of the values of that coordinate and a sum of those values that will be provided from the other failed node. With that, we can set up van der Monde-looking equations for those components and for the sums. And so in the first node, we compute some of the L components of the erasure and sums, linear combinations of the available coordinates and the missing coordinates. For the second node, and then in the second round, these sums are being exchanged between the two nodes to support optimal repair. Let us not say more about this, not to clutter this presentation with even more technical details. Suffice it to say that, again, Reed-Solomon type ideas support optimal repair in the cooperative fashion of any number of nodes. All right? So let me skip through these calculations. Let me move to the very interesting question of repair of Reed-Solomon codes. Forget most of what I have said. Think of Reed-Solomon codes. We are faced with the task of correcting one erasure in the Reed-Solomon code. And suppose we want to meet the cut-set bound or do something similar. How do we do that? So what is the difference now? Now the difference is that the code is not vector, it is a scalar code now, right? The code is linear over the big field. Reed-Solomon code as we know it. We want to correct one erasure. So as basic as they are, this question is completely new. How do you efficiently repair one erasure in the Reed-Solomon codes? This question was unaddressed until 2017 or 2016 as a preprint. The work by Venkat Guruswami and Mary Wooters. It was one of the 3 papers that I mentioned in the beginning, right? That is a paper that set up a new research direction. That paper said, essentially introduced the idea underlying all of the subsequent works on Reed-Solomon repair. They characterized repair schemes, linear repair schemes of Reed-Solomon codes, analyzed full-length repair. Full-length, I will say what it means. There were a number of subsequent works cited here. The work that I would like to advertise slightly more, in slightly more detail is a work with Zach and Min, and that is, it is possible to optimally repair Reed-Solomon codes, so to correct erasure while meeting the cut-set bound. There are some qualifications to that result, but at least it is possible to do optimal repair of RS codes. In the next page, on the next page, I will discuss the Guruswami-Wooters scheme, general repair. Now, it is important to realize that nobody told us that the repair scheme has to be linear. It is difficult to think of nonlinear schemes, right? It is, and so what they did, they said that if there is a repair scheme, then it is basically looks as will be shown now. Characterization of the general repair scheme, linear repair scheme. So we constructed Reed-Solomon codes for single node repair with optimal repair bandwidth. And we derived a lower bound on sub-packetization parameter for Reed-Solomon codes. Jumping ahead, I will tell you what is the answer. So for sub-packetization of RS codes, RS codes or scalar MDS codes over f to the L, 2 to the 6, 2 to the 16, you name it, right? 49 squared, can be repaired can be optimally repaired using a linear repair scheme if, or rather, only if L is omega exp k log k. So L has to be super exponential, right? It's k to the power k. where k is the dimension of the code. Previously it was n to the k, now it's k. Previously it was e to the k, now it's k to the k. And that is what we pay for being able to optimally repair scalar codes, not vector codes. All right? Universality is also there. So the idea was introduced in the paper of Shanmugam, Dimitris Papalopoulos, and Alex Dimakis, 2014. And we vectorized that code. So as I said, f to the l, 2 to the 8. So we consider each byte of the code word as 8 bits. So that is vectorization. And that is my L. Here is, well, an example. I don't know if that's needed. We take a Reed-Solomon code over F16. We consider it as an array code over F2. L is 4. F can be represented, F16 can be represented as a 4-dimensional vector space over F2. And to save on the repair bandwidth, we compress the values of the helper nodes by projecting them on a subfield. So instead of transmitting the entire helper node, we transmit some projection, some function of the helper node. For instance, in the example, let us say alpha is a primitive element of f over f2. So alpha is such that alpha 4 is alpha plus 1. So that's a textbook example of finite fields. And then 1 alpha, alpha square, alpha cube form a basis of f16 over f2. We will need the trace function from f16. So that is what serves these projection purposes. Trace from f16 over f2. Trace is a function of this form. X plus x square, x to 2 to the 2, x 2 to the 3. And that's a linear map from f to b. So the trace takes value 0 or 1, but nothing else. That's a function from f16 to f2. And it is clear that this takes value 0, 1, because take this function, a square of that is that function itself. Squaring does not shift it. And if a square does not shift the function, then the function is 0 or 1, right? So that's why trace is a function from f16 to f2. Importantly, for any element of f16, the values trace c alpha square, alpha cube suffice to recover c. That is, quote unquote, orthogonal expansion of an element of f16 as 4 elements of f2. So the trace values suffice to recover. One is tempted to say Fourier-like expansion. Not exactly, but the idea is similar. All right, so what is the repair scheme of Reed-Solomon codes of Guruswami and Wouters? Let us take a look. It's a very nice, original, and clever development, so let's maybe devote some attention to that. So we have two finite fields, B, which was F2, and F, which was F16. Let us say that the extension degree 4 is now L. Omega is a subset of points in F, so that's the evaluation points for the Reed-Solomon code. The Reed-Solomon code of length n dimension k over F is obtained as evaluations of all polynomials of degree up to k minus 1, evaluations at the points p1, pn. The number of parities is n minus k. Let Ci be erased. Let B1 to BL, Bn, typo, Bn be a code word in the dual code. So the code word in the dual code has the property that its dot product with any code word in the Reed-Solomon code is 0. Let C1, Cn, B1, BL, Bn be a code word in the dual code. Each coordinate of that coordinate is an L-dimensional vector. Let us say that it forms a basis of F over B. As we said, the values of the traces with these basis elements suffice to recover Ci. That is from the previous page, no Well, the only new element is this is a dual code word. So we will use the fact that this is a dual code word. As I said, the dot product with the original code word is 0. And I have isolated the erased coordinate because I don't know this term. I know all of the other terms. So take the sum to the right. Take the trace on both sides. The trace is a linear function. So this is legitimate. To recover, so we have, we have this equality. And we need these values to recover CT. Right? As we said, with the basis, we can recover the erased coordinate. And to recover the erased coordinate, we need the right-hand side. So let BI be the maximum linearly independent subset of the coordinate J1 to L. We can find CI from the union of those traces. So a scheme defined in these general terms, in fact, is the only possible linear scheme. This is quite an impressive result, right? There are no other linear schemes but this one. Is there a nonlinear scheme? Maybe. But the linear schemes have been characterized. Very nice. So the theorem says, a linear repair scheme for coordinate I with bandwidth B exists if and only if there is a subset of dual code words such that the dimension of this space of xi's extracted from the ith coordinate is L, and the bandwidth bandwidth B is at least the sum of the dimensions of these vectors. Okay? If L is small compared to the number of parity symbols, then the cut-set bound is not attainable. There's a trivial lower bound on the bandwidth. And so if the Ritz-Solomon code has full length, which is q to the L, 2 to the 4, then the cut-set bound is not attainable. And then, of course, it becomes an art. There is no simple universal expression for the bound, or at least there is this bound, but this bound is not very helpful for that repair. So repair of full-length Ritz-Solomon codes is a difficult task. There are nice advances. You can expect some nice schemes in particular cases. Probably you cannot expect a universal optimal scheme. It is possible to do universal repair, optimal repair for shortened codes if the length is much smaller than q to the L. I'll show briefly how this is done without going into many details. So very briefly, we do this as follows. To fit the good, so this is now from the work with Min and Tsachi. We evaluate our code at endpoints of the field where those endpoints have the following property. What we want is that none of the alpha i's is contained in the extension of FQ where we adjoin all the other alphas. This is kind of algebraic orthogonality property. We take alpha 1, alpha n are the evaluation points, and what we want is that alpha I is not an element in the field to which we have added all the other alphas. So we have F1 is the field that does not contain alpha 1, does not contain alpha 2, does not contain alpha n. As we attach alpha 1, we get the field F. As we attach here alpha 2, we get the same field F. Then we also need an S degree extension of F, where S is D, number of helpers, plus K minus 1. So this is a rather complicated structure. We evaluate the code at the alphas, and the code is defined over K. Without saying much more, because I want to say something about very different group of problems, I will say that once we consider that Ritz-Solomon code, it is possible that it can be optimally repaired. The only thing that you might want to remember is this construction about algebraic independence of the evaluation points. All right? So this is bound on sub-packetization for the construction, and there is a lower bound on sub-packetization, and so we are sandwiched between n log n and k log k in the value of L for the optimal repair with Solomon codes. All right? I will skip the multiple repair part. This is possible. Let us look at this bottom part of the slide. For vector codes, optimal sub-packetization is L to the power n divided by R. For scalar codes, sub-packetization for optimal repair is doubly exponential. So this is what we pay for doing scalar compared for doing vector repair. All right? Multiple erasures, well, there is more on multiple erasures, but never mind that. Let me see what else I have. Heterogeneous storage. Heterogeneous is also interesting. You see, you start along these lines, questions mushroom. So let us summarize what we said so far. There is local information processing. Of course, yeah? Doesn't have to be obtained by the trace function. That's one possibility. As a subcode, well, yes, of course you can construct some code of which this will be a subcode. So let's think of local information processing. So there is repair degree or access, and then there is repair bandwidth. The operation itself may be erasure correction, maybe error correction. So erasure correction under low repair degree is LRC codes. Erasure correction under bandwidth, optimizing the bandwidth, is regenerating codes. Error correction under low access is nothing but the famous LDPC codes, right? So LDPC codes fit this picture very much. Can we correct errors while optimizing the communication bandwidth? And the answer is yes. Something is possible along these lines. This topic still awaits its development, but at least there was the first paper. There will be one more paper at the ISIT next week by a student who became interested in this question. So you try to correct errors by only acquiring a part of the information available from the received vector. So imagine if you are into communications, right? You transmit over a communication channel, a Gaussian channel. You have received something. You try to recover the message, but you recover it not from what you have received, but from some function that eliminates some of the information out of the received coordinates. That is error correction from partial information. And at least in the algebraics, the problem has been set up, and it has some results were obtained there. I invite you to take a look. Maybe something will happen. All right. No, the other direction. Heterogeneous. Well, I have much more than I will present. But let us look at this picture. So we saw those what is it called, wardrobes with hard drives in the very first picture. There is a closet with storage drives, and there is another fixture that carries the drives, and one more, and they fill this room. Arguably, at least that's what you read when you read systems designer's view. Talking within one closet is more difficult than talking between the closets. So one such thing is called a rack. The drives are put on a rack. Let us say communication within the rack is free. And communication between the racks is the only thing that counts toward the repair bandwidth. That is heterogeneous storage. Communication between some vertices in your graph is easier than between the other vertices. Let us say, moreover, that, so let us say a node in a rack has been erased, and we want to repair it by contacting the nodes available within the rack and the nodes on the other racks. So this is the picture of this rack-aware model that was introduced a few years ago. That is by far not the only model of heterogeneous storage. You can think of other models. For instance, it is simply, there is a group of privileged nodes, and talking to those nodes incurs more of the cost in terms of the repair bandwidth than talking to the other nodes. That was one of the first models introduced in this heterogeneous context. Well, sticking to the rack, let us say that before communicating the repair information to the failed node, we are allowed to do some processing of these nodes on the rack. And so this is free, and then what we communicate is the function of all the nodes within the rack. And then again, the cut set bound is possible, and the repair scheme is possible, optimal repair, all of this can be done. This is the cut set bound, so D bar here is the number of helper racks now, not the helper nodes, but those wardrobes that communicate information as a single unit. And so on and so forth. Perhaps I should not say more apart from this definition so that you are aware of the other versions of the problem. There is an algebraic construction that is a combination of the work with min, and we inject here the multiplicative structure of the field. It plays a role. And if you think of it just a little bit, it is clear why multiplicative comes into the picture. It is the size of the rack and the number of nodes in the rack that play out as a single unit. And so we divide by that number, and that translates into using the multiplicative structure of the field in the repair equations. So this is work with Chen Zitan, which will be presented in Paris next week at the ISIT. MSR codes for the rack-aware model. This direction, I don't know if I would invite you to look at that in my mind, these heterogeneous models, at least in this variation, are of some interest, but maybe not the central questions. Well, who knows? I should not discourage you completely. Interesting things can always happen. I view this as a variation, but maybe you will view this differently. So I will mention this, and I will proceed to the next. Yeah? Any questions here? All right. Let me abandon this algebraic context altogether. What are the new directions that I would like you very much to pay attention to and maybe even to consider? So most questions that will be mentioned now are open. So what is the main idea of all of these regenerating code models? We represent information in a network, and we recover the information based on the information in the other nodes of the network. That was the main idea behind the models presented so far, and, well, many other models that we cannot cover here. As we said, all the problems considered so far assume total connectivity. Any node can talk to any node, well, apart from the cooperative model where we not as much forbid communication, but we say, well, if you want to talk here, then you pay more for the bandwidth. But let us say that it's simply impossible to talk. Communication between some nodes is impossible. So let us say there is a graph. One version has been discussed, this storage capacity of repairable networks, right? Where you look at the neighbors. But let us say we allow ourselves some helper set, not necessarily the neighbors. So there are immediate neighbors and there are second, quote unquote, degree neighbors. So the second degree neighbors provide information to the immediate neighbors of the vertex. How should the protocol be set up? Should the immediate neighbors process that information, or should they relay it? I have no idea. I have no answers whatsoever. Let us say, consider the following repair question. So far, we have had a complete graph. I remove one edge out of that graph. What can you say about repair? What is optimal repair? What is the optimal bandwidth? I don't know. So should we, as we said, should we relay or process? Let us say the connection graph is random, like the Erdős-Rényi graph, right? You inject edges and you examine whether the graph is connected or not, and there is threshold for connectivity. Is there a decent way to think of threshold properties for repair, the repair question? Well, let us say the links carry errors, random errors. There was one version of that discussed in the algebraic part in the optimal bandwidth construction, but let's say there are random errors in the links. Let us say in this protocol there were nodes that were overtaken, and they provide deliberately incorrect information. And moreover, whatever is handled to them, they also distort in an unfavorable way before passing to the node being repaired. Each of these questions can be fledged out into a problem, but no solutions are available at all. Dynamical models, so the network evolves in time. And there was a very nice paper by Ziv Goldfeld, Guy Bressler, and Yuri Polansky on the Ising model. I will not say more about that. That would take us too far. That is one of the dynamical models. I will present you a simpler dynamical model right now. And that is something that I have been doing recently with Ohad Elish, a postdoc in Maryland. So the previous case analysis that we discussed was the worst case. Min cut, that's it, right? Min cut gives, that is the worst case, that is the worst that can happen. Min cut already determines the largest size of the file that can be stored. But nodes fail and keep failing, so the evolution of the network occurs in time. And it is a reasonable assumption that the nodes fail, let's say, at the Poisson, independent Poisson rate. So each of them observes the Poisson arrival process, and whenever there is an arrival, the node fails. What's the rate of that arrival? Well, that's commensurate with the failure probability in the network, right? And the question is now, what is the time average size of the file that you can reliably store in that network, given that stochastic process of failures? And it makes sense to assume that some of the nodes contribute more symbols to the file recovery than the other set of nodes, so upper and lower to follow the mnemonics. And then it is possible to show that the average size of the file is probably higher than the worst case. So the random nature of the failures combined with this heterogeneity in the contribution from the files, from the nodes, enables one to store more information in the network. There is a new set of tools completely. There is nothing algebraic here. There is a Markov random walk on the permutations of those failed nodes. And there are theorems about the mixing time of Markov chains. So it moves it in a different direction, which I found appealing. Only the first step. Again, many questions here are completely open. And that's, I guess, a good time to end it, right? Because we have covered a large number of topics, and it's time to celebrate.
Is this on? Yeah? Okay. Any questions?
Now, let's go celebrate.
Yeah, right. Oh, one, so yeah, please.
So what if we measure the difficulty of repairing with respect to the information bits and not with respect to the coded bits?
Yes.
Would that change the answer in terms of the trade-offs that we can achieve?
Not terribly, no. That has been considered. Information locality, all symbol locality. There are variations, but no major changes.
So in particular for Reed-Solomon codes, the repair regime doesn't change?
Nothing changes, no.
Any other questions? Scan. I have no peripheral vision, so just scan. Okay, great. So let's thank Sasha again.
Thank you very much. Thank you.